All right, last time we started this section that talked about algorithms, ways of doing. In this case, we were talking about addition and subtraction. There's a couple other things in this section that we're going to look at. The first thing we're going to look at is doing those same algorithms for addition and subtraction, but in other bases, because I know you guys were so sad to leave those other bases behind. And I don't mean like Babylonians and stuff like that, but I do mean in base 8, or in base 6, or in base 12, things like that. We're also going to take a look at mental estimation and approximations as well, which are different. They're different than one another. Sometimes people try to lump them together, and they do sort of occur together in our notes. But we will talk about the difference and reminders of that when we get there as well. I can't find my stylus. Just a second. All right, so last time we had left off on equal additions and talked about it being this very important idea of not borrowing. And now we're ready to take a look at what happens in other bases. Okay, so we're going to start on this one with base 8. And there's a reminder at the top that base 8 has the numbers from 0 to 7. Those are the numerals. And we're going to add 3, 4 base 8 to 1, 7 base 8. And on most of these, I'm going to show two ways of doing the problem, both the standard algorithm, because that's the one that you are most familiar and comfortable with, and then one of our newer algorithms that maybe you just learned last time, okay? So you can see sort of a compare-contrast. So on this one, we're going to take a look at the standard algorithm, 3, 4 plus 1, 7. And if we were looking at the standard algorithm, we'd start with the right-hand column, right, the ones place. And we would say 4 plus 7. And what is 4 plus 7? Just simple, what is 4 plus 7?
11.
It's 11. Okay. So when we work in our base, though, and we get a number that's bigger than the base, and 11 is bigger than 8, we do this thing where we carry or we regroup to the next column, right? And we do it very nicely because we have a 2-digit number at that point, and so we just move one of the digits over, which kind of looks mysterious as to why is that digit moving or what's really going on behind it. But we did talk about that last time. The reason we're moving that digit is because that's how many 10s there are, right? There's 1 10 being moved over. So on this one, when I end up with the number 11, the number 11 is 1, 8, and 3, I should write it differently. Let me write it this way. It's 1, 8, plus 3 ones. Okay, the ones, the 8s here, these are our base system that we're doing. So I'm trying to figure out how many 8s do I have that I need to carry over, and I have 1 8 that I'm carrying over. And then I have 3 ones that stay in the ones column. Okay, that's one way to think about it. An alternate way to think about that is you could count like kids count on their fingers, all right? So you usually start with a bigger number, 7, right? And you go 7, 8, 9, 10, 11, right? They do this with their hands, don't they? You know what I'm talking about, right? You guys are smiling like you do it too. Do you do that too, Holly?
I was just taking me a minute to understand.
Oh, okay. All right, so a lot of kids do count on their fingers, even beyond the age when they should be counting on their fingers. My 4th grade daughter counts on her fingers still. And it's a tough habit to break when you're used to it as well. So when she would do this problem, if she were working in base 8, which I recognize that's not where she is, but how you would do it if you're counting on your fingers, is that when you have the 7, the next digit after 7 in base 8 would be 1 0, 1 1, 1 2, 1 3. And I've counted up to 4 on my hand, and I'm at 1 3. So that's another way of doing this same problem. Instead of breaking it apart into 8s at the end, it's to remember what my digits are in base 8. What comes next? Once we get to the 8s column, 1 plus 3 plus 1, that's no problem because I've got 5. The number's smaller than the number 7, so I'm good to go. And the answer is 5, 3, base 8. Make sure that your answer includes the base subscript, 8. Okay, so I'm going to go a little off script. We're going to use one of the other algorithms, one that I haven't normally done with this one. Let's do the expanded algorithm. Okay, so the first one is standard. This is the standard algorithm. Okay, so the expanded algorithm says what? Well, it says I have 3 times 8, 3 eighths, plus I have 4 times 1, or 4 ones. And then I have 1 times 8, or 1/8, plus 7 times 1, or 7 ones. That's what it says. And when we talked about this, we said we could actually add straight down from here. So like I have 4 eighths now, and I have 11 ones. But the 11 can be broken apart, right? Just like I did in the previous way I did the problem. It's 8, I'm sorry, I said that wrong. It's 1/8, and it's 3 ones to make 11, plus the 4 eighths at the beginning. So there and there you see that I have my 5 eighths, plus my 3 ones, and those values here and here are the same digit that I got from before, of course. It's 5, 3, base 8. Okay. We're going to do a subtraction one next. Still in base 8. Okay, once we sort of focus on a base, I like to do a couple of problems in there before we sort of shift our gears again. 3, 4 base 8 minus 1, 7 base 8. Okay, so again, I'm going to do the standard algorithm first. So this is 3, 4 minus 1, 7. So you're all very familiar with the fact that I'm not going to be able to take 7 away from 4 in the ones column, so I have to regroup or borrow. So in the regrouping or the borrowing, the 3 becomes a 2. But this is base 8, so when I borrow in base 8, I borrow 8. Okay? What is 8 plus the 4 I already have? It's 12. And now I can do subtraction just like I would have before. The borrowing part is what causes people to get tripped up, because when I'm borrowing, I'm only borrowing 8. Okay, so I can do 12 minus 7. What is 12 minus 7? It's 5. And then 2 minus 1 is 1. And this is base 8. Okay, and again, the reason that's happening is because when I'm regrouping and I'm borrowing in whatever language you want to use, I have a different place value I'm borrowing from. I'm borrowing from the 8th place. All right, let me show you what happens when we try this with equal additions. That's the last algorithm that we looked at last time. Okay, so what was the whole point of equal additions? No borrowing. Okay. The goal, the point, is no borrowing, and we do that by taking whatever we're subtracting from, that we can't subtract from it, and turning it into a 0. Okay? I mean, that's what we're going to do. We're trying to turn it into a 0. What would I need to add in base 8 to the number 7 to turn it into a 0? That's in base 10. We're in base 8. 1. Why is it 1? Well, because normally 7 plus 1 is 8. But in base 8, 8 would then have to be moved over into the 8th column. And if I add 1 to the bottom, I have to add 1 to the top, so I have 3, 5 on top. The number after 1, 7 would not be 1, 8 because there's no 8s. It would be 2, 0. And I can subtract nicely now, 3, 5 minus 2, 0 to give me 1, 5, base 8. And on this problem anyway, not every problem, but on this problem, equal additions is easier. There was fewer steps, it was more efficient. I had less going on than I do when I'm actually using the standard algorithm with my borrowing and my adding my digits together and then subtracting it out. Okay? Holly?
How come we learn this?
How what?
Why do we learn this?
Because you're probably going to have a curriculum that's going to make you teach it. That's the best answer that I have for you. It's not the only answer. For some kids, the borrowing concept's really, really difficult. And if you had a child who never learned to borrow, but they could do the subtraction in a different way, wouldn't you want to have that available? Yeah, and that's the real answer. I was kind of being silly before, but there are curriculums, and your students will have them if you happen to teach at the grade level that teaches this. I've seen them come home for my kids, so you're going to see them. Yeah, and you'll probably see others that that we're not teaching right now come across your path in 10 years from now, and you'll be like, I don't know what they're doing. And the idea is that you're going to learn. And so, no, you probably didn't. No.
Okay, so using base 8 is just so that we see how they're looking at it.
Yes, and maybe that's part of what you're asking too. Using the different bases, the point of us doing the different bases in here is not because you're going to teach different bases to your kids. What the point is for the base edition is for you being able to put yourself in a position that feels a little bit less comfortable, both with your standard algorithm and with the base system that you use all the time, so that you can actually kind of have some sort of sense of what your students are going through when they're learning it too. Because they're not near as familiar with base 10 as you are, because you've been using it now for 20 years, right? So that's the idea. Okay, we're going to switch bases and we're going to try a couple more. We're going to do base 3 next. Okay, only 2 more bases. This is it, just these 2 problems, and we're going to shift the gears. But we're going to do base 3. Base 3 is just got 3 digits, right? 0, 1, and 2. We don't have a lot to work with here, so we end up borrowing and carrying a lot when we're working with smaller bases because we don't have as much to work from. On this one, we're going to do addition. I'm going to do kind of like what I did last time. We're going to do the standard algorithm first. So in the standard algorithm, I have 1, 2, 1, 2, plus 1, 1, 2, and I'm working in base 3. So we start with the ones column, right? 2 plus 2 is 4, but 4 is how many 3s? It's 1 3 and 1 left over, or 1 extra. 1 3 and 1 1. All right, next column, the 3s column. I have 1 plus 1 plus 1, and that is, it's 3, which is 1 in the next column over, and 0 left over. Right, I've got 1 3, so I carry it. All right, next column. This would be the 9s column or the 3 squareds column. 1 plus 2 plus 1 is 4, right? Which is 1 3 to carry over, and 1 left over. And then finally in the 3 to the 3rd column, I have 1 plus 1, which is 2. So this is 2 1 0 1 base 3. Good job. Let's take a look at it in a lattice algorithm. So in the lattice algorithm, I have 1 2 1 2 1 1 2. You'll remember that we have a box underneath that's got as many places as the digits in our numbers we're adding. We have a 4-digit number and a 3-digit number, so I need 4 places. So I need 4 boxes. And then I split my boxes diagonally, like so. Okay, everybody good so far? Okay, so the lower box is my 1's place, and the upper box is my 3's place. So when I'm adding them, I've got a question of how many 3's do I have, how many 1's do I have. So in the first column, 2 plus 2 is 4. So 4 is 1 3 and 1 1. The next one I have 1 plus 1, that's just 2 1's. And then I have 2 plus 1, so that would be 3, making it 1 3 and 0 1's. And then I have the number 1. Okay, if I were doing this problem and I were working base 7, the top box would be the number of 7's and the bottom box would be the number of 1's. If I were working in base 12, the top box would be the number of 12's, the bottom box would be the number of 1's. Okay? So let's finish this now. We do that by extending the diagonals, and we're going to add along the diagonals. We have to start on the right-hand side. This is a 1, right? I do have, let me move this down just a little bit so I have a little bit more space. That wasn't what I meant to do. Try it one more time. I do have in the next column, diagonal column if you will, 2 plus 1, which is 3. There's no 3's. So I have to write down a 0 and carry a 1. I do sometimes have to carry even in the middle of lattice if the numbers get too large. Most of the time they don't, but if they do, right, anytime I pass 3, I have to carry here. And then my next column, right here, would have the 1 and the 0 in it, so that's a 1. Oops, I think I lost my 1 along the way. And then I have my last column on the far left, I have 1 plus 1, which is 2. So 2, 1, 0, 1, base 3. Is it good? Okay. And a subtraction problem. So we're going to subtract the same way in base 3. So I have 1, 0, 0, 2 minus 1, 1, 0. So in the ones column on this one, I'm sort of lucky, right? I can do it. I don't have to do any worrying about regrouping. It just subtracts and I get a 2. So I got that one to work out nicely. After that, not so nice. So in our next column over right here, I can't take 1 away from 0, so I'm going to have to regroup or borrow. The problem is that there's nothing to borrow from if I move 1 to the left, so I have to keep moving. So the 1 that's in the far left column will become a 0. But when I borrow in base 3, how many do I borrow? 3. I borrow 3. Now that there's a 3 there, I have enough to be able to take away 1 from the 3, right? To borrow a 3 for the second column from the right. The 3's column is what it really is. All right, and then I can subtract. So in the second column from the right, my 3's column, 3 minus 1 would be 2. In my 3 squareds column, which is the 2 minus 1, I would get 1. And then in the 3 cubes column over here, there's nothing left. So the end result is 1, 2, 2, base 3. And while I have other algorithms I could do, I want to show you equal additions again, so you can see how it would work when I have to do more than one step. Okay, so again, there's nothing wrong with the ones column, so I'm skipping the ones column, and I'm trying to move over to the tens column, not tens, excuse me, threes column right here. So this is where I am, and I'm trying to figure out what I need to do to add to this 1 to make it a 0 in base 3. So what would I have to add to 1 to get 0 in base 3? 2, yeah, and the 2 is in the right column, making it a 2, 0, yeah. So we're going to add 2, 0. So now I have 1, 2, 0, 2 on top. And this is already a 0. This became a 0. And I have to make the other digit to the left of it 1's bigger. So this is 2, 0, 0. Yes, Colton.
Wouldn't the top number be 1022?
Got it in the wrong spot. Thanks for fixing that. You're right. I just moved too quickly. Much better. Thank you.
Yep.
Okay. All right, is everybody okay with that now? Lovely. I still have a problem though, right? I can't subtract that column now. So what would I have to add to my 2 in order to get it to become a 0? A 1, because I'm working in base 3. And it would be a 1 in the correct location, so it would be 1, 0, 0, right? So as I do that, so this one resulted in this. I now have 1, 1, 2, 2. And there's already zeros here. And then the 1 and the 2, right here, oops, would add together to be a 3, which would then bump into the next column over. So I have 1 with 3 zeros following. 1, 0, 0, 0, which I then can subtract without borrowing. 1, 2, 2, base 3. We're not spending like the entire section and doing it on other bases, but you will have a few problems to give you a sample of that. You will see some on your test too. You'll have at least one problem on your test that will be done in another base. So just letting you know that. All right, so let's shift gears, do something different. We're gonna do mental math next. Okay, so one thing about mental math is when something says mental math, it does not mean estimate. All right, it means do it in your head. Yeah, that's the goal. So it means something that you can do without having to write things down, but you're going to write them down so that I know what you did. All right? But it doesn't mean to change the value so that you're just getting an approximation. Sometimes there's a misconception there. So I'd like to show you a few different mental math strategies. Some work better for people than others, and I totally recognize that. So some of them you're going to be like, ooh, I like that one a lot, and somebody else is going to be like, I don't get that one at all. That just is not how my mind thinks, and that's okay. So the first one is called, is adding from left to right. So in this algorithm, if we're adding 46 plus 38, and as I've done before for you, I tend to think about it adding like this. What we do is we add the 40 plus the 30 together. We add the left-hand column. So that would be 70, right? And then we add the 6 plus the 8, which would be the right-hand column, and that's 14. Because single digits are easier for us to add together in our heads. I can add 4 and 3. I can add 6 and 8. And then I can add one more time. I've done 3 separate additions. 2 of them were single digits in my head. And the third one compiles all of it together. So 70 and 14 would be 84. Okay? So that's adding from left to right. It's all right. The next one I like a little bit better. The next one's called breaking up and bridging. So what we do with this algorithm is that we add the 46 that we're starting with, that we started with, to the 30 from the next value. So we have 76, which we usually can do that one pretty well in our head. I think most of us would be all right with that. And then we'd add 8 to that. So it's not single digit addition at this point. I am going to have to borrow, or not borrow, but carry and so forth. But it's one time of it, right? And I'm not doing it a 2-digit number. It's a 1-digit number added to what I already have. And I would end up with, again, 84. So that's called breaking up and bridging. Okay, the next one is called trading off. Trading off is similar to equal additions. So jot that down for yourself. Trading off is what I do every month when I create a budget in my home. There's only so much money, and I can't increase eating out unless I decrease something else, right? That's the idea for trading off. There's a trade-off, right? There's a trade-off in all of our lives. When we spend 2 hours playing around on Facebook or Snapchat, we can't spend that 2 hours studying for Civ. Yes? Yeah. This is the algorithm. So what we do is we take our 46 and our 38, and we really want to get a 0 somewhere because zeros are the best. So we either add or subtract to make that happen. In particular on this one, the easiest way to do that is to add 2 to 38. But if I add 2 to 38, it means I take away 2 from 46. That's my compensation. Adding to 38 is friendly because I end up with 40. Subtracting from 46 is not too bad. I end up with 44. And then I can add the results together because they are friendlier add-ins than I started with. Okay? Trading off. All right, all of the algorithms we've done so far, these 3 mental math algorithms, work really well when you're doing just two values added together. Okay? Compatible numbers, the next one you'll notice, means I have a bunch of numbers added together. Compatible numbers doesn't make a lot of sense with just not two digit, but 2 numbers being added. So compatible numbers is the idea that some numbers add up to nicer values than other numbers do. In particular, it's really nice to add 70 and 30. Why? Because you get 100, right? What else is really nice to add together here? 40 and 60, because you get 100. So usually compatible numbers add up really nicely to give you 10 or 100 or 1,000. I mean, that's kind of the deal. So I end up with 100 on the top, the first two I marked, and the 100 on that bottom. And then the one that's sort of missing at the moment is I didn't ever add in the 50. So if I add all of those results now together, what do I have? 250. And it's a lot faster than saying 40 plus 30 is 70, and then I have to add 70 and 50, which is an awkward addition, and then I have to add another 70, additionally awkward, and then another 60, right? That's not the easiest way to do it, but pairing up numbers that are nicer is a much friendlier strategy. When you don't actually have compatible numbers, you can also make compatible numbers. So here's an example of making compatible numbers. 35 and 68 are awfully close to compatible. If we shifted one of them just a little bit, and we have to compensate for the shifting, we don't just get to like change the number and not pay for it, right? Like we pay for the changes we make. But we don't pay much. So can you think of a number that's nicer to add to 35 than 68?
5,
Okay.
40 and 60.
What were you thinking?
40 and 60.
40 and 60 would be nice. Then I'm changing both of them, which is okay. 70, 30 would be nice, but I'm still changing both of them. Can we only change one? Somebody said it. I heard somebody say it. What?
Or 35.
35 and 65 actually is not the right one, but is a nicer one. Any of the ones you guys picked are okay. I'll do one of them so you can see what it would look like. But let me show you the one that I had in mind, because I would like to only change one number if I can. I'd kind of like to do 35 and 65. 68 is not the same as 65, but it is the same as 65 plus 3, right? 35 and 65 is 100. Now I have 103. Now let me do the example you guys said with 30 and 70. Okay? If I wanted to change it to 30 and 70, in fact, I'm going to move that over here. The only way that I can do that is if the 35 becomes 30 plus 5, and the 70, in fact, let me just add it down right here. And then the 70, which was previously 68, becomes 70 minus 2. Do you see I have to pay for it twice because I've changed two numbers? So this is still the 100, and this is still 3, so I still get 103. I just have to compensate twice instead of once. It's not that you can't do that. I think you can do that, and I think that's still mentally able to be done. It's just one additional step. Okay, is that all right? I have one more on this page. This is breaking up and bridging. We already had this breaking up and bridging, but we had it for addition. This is for subtraction. So breaking up and bridging with subtraction works the same way. I take the original value started with 46, and I subtract the tens digit. So what is 46 minus 30? 16. And then I subtract off the remaining 8 that I previously did not subtract off, because 16 minus 8 is not as hard as doing subtraction of 38 at the beginning. So 16 minus 8 would be 8. It boils things down into single digit kind of stuff. Okay? Trading off is the same. This trading off with subtraction is exactly the same as equal additions. Okay, so this is also equal additions. When I'm adding two numbers and I'm doing trading off, I have to add to one and subtract from one. When I'm subtracting numbers and I'm doing trading off, I just add or subtract from both of them. So 46 minus 38. Again, the goal is to get things to be a 0, so I would add 2. So this would be 48 minus 40 for a value of 8. It's just equal additions, just another name for the same thing. Okay. Dropping the zeros. 4,600 minus 3,400 both have zeros in the tens and the hundreds, tens in this ones column, right? So the idea is that these zeros are rather unimportant in terms of the actual subtraction going on. And I can rather ignore, pretty much ignore them, right? So what is 46 minus 34? It'd be 12. And then my answer would be 1,200 since I had the zeros that I ignored. Make sense? Okay, so I made a big deal about it when we started mental math, that mental math is exact computations we do in our head. It's not changing values unless we compensate for them, right? I'm actually getting the real answer. But we're also going to look now at estimation. Oftentimes, estimating what the answer should be is a good idea in general. So like some of the tests that I gave you guys back when you were adding up all the numbers together, there were a few of you who were telling me that when you were doing Gauss's method to add numbers together that you were getting decimals at the end. You should have recognized, I can't add whole numbers together and get a decimal. It doesn't make sense. There's something going on that's sort of conceptually inaccurate. I don't know what my error is maybe, but this can't be right. So estimation allows us to do that. It allows us to look at something and say, does this make sense? Or is it so far off that something weird is going on? I need to re-examine it. So I'm going to show you a couple of different ways to do estimation because rounding is not the only way to estimate things. This first one is called front-end estimation with adjustment. And so here's how it works. We have 332, 462, and 225. So front-end estimation simply adds the first digits together and zeros everything out. So 300, 400, 200. Okay? Front-end estimation takes the first digit. So 3 plus 4 plus 2 is 9. So I'm starting off with 900. So this is the front-end estimation part. Anytime I ask questions about adjustment, people would like for it to be just the same as what I just did, but it simply isn't. Adjustment means taking the values that I'm left with, I'll write them all down, 32, 62, and 25, and trying to form approximate compatible numbers. So are there any of those numbers that are approximately compatible? Like they almost add up to 100 or 1,000 or something. Yeah, these two right here, 32 and 62. They're not exactly 100, but they're pretty close, right? They're pretty close. This is approximately 100. Okay, that's the adjustment factor. This number, you can round it off at the end if it's a number that's weird, like if it said 28, we might not write down 28. You might change it to 25, or you can leave it the same if it's fairly nice already. So I really now have three values on the screen that I'm adding. I have 900, 100, and in our case 25 is pretty nice, so I'm going to leave it. And if I add 900, 100, and 25, what do I get? 1,025. And it is an estimation, for sure, right? The estimation actually took place, the inaccuracy took place right here. But we're okay with that because that was what we were asked to do. We were asked to estimate. All right, so the next one is much like compatible numbers. We're grouping them together, kind of like that adjustment part at the end of the last problem. I'm trying to group them together so that they're approximately compatible. So taking a look at these 5 numbers, sometimes there's more than one way to group things, and that's okay. So what are 2 numbers that I could say are approximately compatible? They almost add up to 100. 35 and 70, okay. So we would like for these to be approximately compatible. So these are approximately 100. What else?
42 and 64.
All right, 42 and 64 are approximately compatible. And then again, you can either leave the 55 as 55, you could round it down to 50. I don't care. It really doesn't matter. We're estimating. So if I add the 100, and the 55 or 50 or whatever together, I will have an approximate answer of 250 or 255 if you prefer. Okay. Is it in the ballpark? When you actually grab your calculator and you added these together and you end up getting 2,056, there should be some sort of red flag that goes off and says, that didn't make any sense. Somehow I put a 0 in there wrong or something. Something happened. The calculator didn't understand what I meant. Clustering. Clustering, again, only works in certain cases. Clustering works when the numbers are all pretty close to the same number to begin with. Okay, so this is good when all values are approximately the same. It doesn't really work otherwise. What value are all of these values approximately the same as? Well, it's 500. Yeah, they're all about 500. I realize that some are closer than others, but they're all sort of clustering around 500. If I like drew a number line and I plotted them on the number line, they would all be sort of in the ballpark of 500. Does that make sense? They're in the same neighborhood. So they're all about 500. And there are how many of them? 5. So what is 500 times 5? Yep, 2,500. All right, 2 more. Rounding, which you're very familiar with. Some of the time, I don't know why your book does this, but it doesn't tell you what it wants you to round to. It just says round. So, you know what the cool thing is about the word round? If they don't tell you, it means you get a pick. Right? So, if you get a pick, the easiest thing to pick here would be the thousands place. So, if you remember, when we're rounding to the thousands place, we look at the number after the thousands place. In this case, would be the hundreds place. If it's 0 through 4, we zero everything out at the end and we round the whole number down to 4,000. If the number is 5 to 9, we round everything up by rounding the 4,000 at the beginning to 5,000. So if we're doing the thousands place on this one, I have 5,000. And whatever I do for one value, I'm doing for the other one too. So this is a 3. And I look again at the hundreds place next to it, a 1. So this one will round down. So everything after the 3 becomes a 0. So this rounds down to 3,000. And my value then would be 8,000. If it said that it wanted you to round to some other place, like maybe the hundreds, let's try that one. Okay, so the hundreds place means I'm going to have the 4 at the beginning, and then this 7 will either be a 7 or an 8. And that's determined based on the next digit, the 8. So will the 7 become 4,800, or will it stay 4,700? Yeah, it will round up to 4,800. And then on the second one, I have the 1, and the next digit is a 4. So will this stay 31 and then become 100, or will it go up to 3,200? 3,100. And then if I add, you'll see that I get 7,900. Obviously still fairly close to the 8,000 that I got with the thousands place rounding. Last one. Are you ready? Range. All right, so using the range. Range is a method for giving you a low end and a high end for where the answer actually lies. So if somebody asks you, so how much is your monthly income? You can say, oh, well, it's between, $4,000 and $5,000 a month, depending on what happens in my bonuses or whatever, like if somebody's talking like that, right? They talk about a low end and a high end. And that's what a range is. So what the range does is the range says, oh, look, 370. Well, 370 is between 300 and 400. 647. Well, that's between 600 and 700. And it adds those two results together because this one said addition, right? I'm adding. 300 plus 600 is 900. 400 plus 700 is 1,100. So the range is 900 to 1,100. So it does a round down on one half, it does a round up on the other half, and it says, hey, the answer is going to be between those values. And that's all it is for range. All right, we only have 5 minutes for group work, but I'd like for us to go ahead and do it because that way you don't have homework to do over spring break, because I know you don't want homework to do over spring break, do you? No, you don't. So go ahead and find your group work partners. There are 4 group work problems, and then the homework for this section will be due on Friday.